In this video, we present the solutions to homework number 5. In problems 1 through 6, we want to determine if the limit as x goes to 3 of g of x exists, and in each of these pictures, the function g of x is represented. Let's go ahead and start taking a look at the first one. So looking at number 1, if we approach 3 from the left, meaning we plug in values to the left of 3 but getting closer and closer to 3, we can see that the values will approach 2, or the output values will approach 2. So as we approach 3 from the right-hand side, it looks like the limit is approaching 2. But if we approach 3 from the left-hand side, and we start evaluating these, we get that the function seems to be outputting larger and larger negative numbers. So the limit from the right-hand side does not exist, therefore the limit does not exist. And we can go ahead and write the limit as x approaches 3 of g of x does not exist. Alright, let's go ahead and look at number 2. Looking at number 2, as we approach the value 3 from the right-hand side, you can see that the output values are getting closer and closer to 2. Notice the output values are shrinking and approaching 2. Also, while we approach from the right-hand side, the output values are also approaching 2. So you can see that the limit exists and that it equals 2. So the limit as x approaches 3 of g of x in this example equals 2. It's worth noting that the function itself is undefined at 3. G of 3 does not make sense, but that does not mean that the limit can't approach 2 at that point. The function does not have to exist at a value for the limit to exist at a value. Alright, let's go ahead and move on to the next one. And looking at number 3, we can see that near 3, on both sides of the function, whether you're at the right or at the left, the output values are close to 1, and they get arbitrarily close to 1. So we can say that this limit exists. The limit as x approaches 3 of g of x equals 2. Equals 1. And that's because this value here is 1. Alright, moving on to the next one. We can see number 4. And as the function approaches 3 from the right-hand side, we can see that the output values are approaching 3. In fact, they are consistently 3. As we approach 3 from the left-hand side, we can see that the output values are consistently 5. So from the left-hand side, you approach 5, and from the right-hand side, you approach 3. So we have the limit as x approaches 3 of g of x does not exist. because it's not the same from both sides. Moving on to number 5. You should be able to see that around 3, if you approach from the left-hand side, your output values are getting closer and closer to 4. While if you approach from the right-hand side, the output values are getting closer and closer to 5. So the limit from either side is different, and we can say that the limit does not exist for that reason. So the limit as x approaches 3 of g of x does not exist. And finally, moving on to number 6, you can see that as you approach from the left-hand side, closer and closer to 3, the output values get larger and larger and larger as you approach. So the limit doesn't exist from the right-hand side because the output values get larger and do not approach a value. And the same story from the left-hand side. As you approach 3, the output values will get larger and larger from both sides. So here we can say that the limit as x approaches 3 of g of x also does not exist. And that brings us to the end of these problems. Let's go ahead and move on to problem number 7. For problems 7, 8, 9, 10, and 11, we want to determine if the limits exist and compute the limits if they do exist. So looking at this limit, the first thing to notice is that the inside of the limit, 1 minus 6x, is a polynomial. So we can go ahead and make use of our polynomial rule for limits, which states that if you have a polynomial, if p is a polynomial, then the limit as x approaches a of that polynomial is simply the value of the polynomial at a. So making use of this, we have our limit equals 1 minus 6, and then we'll plug in the 1, because the 1 is the a, which is 1 minus 6, which is minus 5, and we have our answer. Just to reiterate, we have a polynomial. So to evaluate the limit of the polynomial, we simply plug in the value we're approaching into the polynomial. And we have our answer. For number 8, we have a fraction of polynomials. Now when dealing with a fraction, with a function over a function, you need to be careful if the denominator is approaching 0. If the denominator is approaching 0, you may have problems. In general, if the denominator approaches 0 but the numerator does not, then the limit does not exist. Notice here that the denominator approaches 0 but the numerator does not approach 0. What I mean by this is if we plug 2 into the denominator, we have 0, and if we plug 2 in the numerator, we have 2. So this limit does not exist. And we can move on to the next one. For number 9, we're taking the limit of this function here. Now is a good time to start making use of some of our limit rules. And I've gone ahead and written those here for you. The limit rule I would like to take a look at is this one right here. This states that if we are looking for the limit of a function raised to a positive power, then we can simply evaluate the inside of the power and raise it to the power. This of course requires that the inside here is something you can raise to the power. So let's go ahead and use that in our problem. So in order to best apply this to our problem, it's nice to recognize that what we're looking at is the limit as x approaches 3 of x squared plus 16 to the 1/2 power. Now we have to be careful because if the inside here is a negative number, we can't raise it to the 1/2 power. So as we go through the next few steps here, we have to keep that in mind. Now let's go ahead and bring the limit inside of the fractional power like the rule here says we can do. We can simply bring the limit inside the power. we have to then be careful to make sure that once we take this limit, it is something you can raise to a power. If it isn't, then this limit doesn't exist. But let's go ahead and find out if it is. So what we get then, bringing the limit inside the power, is the limit as x approaches 3 of x squared plus 16, all raised to the 1/2 power. This means that we can simply take the limit first and then square root it and get our value. That is only if the limit inside here is a positive, because you can't take a square root of a negative number. Now notice the inside here, x squared plus 16, is simply a polynomial. So to evaluate this limit, all we have to do is plug 3 into the polynomial. And we get 3 squared plus 16 to the 1/2 power, which is 9 plus 16, which is 25, to the 1/2 power, which is 5. Notice right here, if this had been a negative number, then we would have that the limit does not exist. All right, now let's move on to number 10. So right away, after looking at this, we can see that we have a polynomial inside the limit. So using our polynomial rule, we can simply plug the 4 into the limit and get our answer. So this will be 4 cubed minus 7, which is 57. And now let's move on to number 11. So looking at number 11, we see we have a rational function, a polynomial over a polynomial. And if we evaluate the fraction at 5, the denominator is equal to 0. 5 minus 5 is 0, but the numerator is not equal to 0. So we have a denominator that's approaching 0, while a numerator is getting close to a number, which means this does not exist. Okay, let's go ahead and take a look at number 18. Now this is very similar to the last one, except for one key difference. Notice if we plug 1 into the denominator, we have 0. But if we plug 1 into the numerator, we also have 0. And that means there's some more work to be done on this limit. What you should do in this situation is try to factor the numerator. And if you factor the numerator, you see that you have the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1. And you can see that these cancel, leaving with the limit as x approaches 1 of x plus 1. So this is just a polynomial, meaning we can plug the value in, and we have our answer of 2. And now we're going to move on to 67, 68, and 69. For 67, 68, and 69, we're going to be evaluating the limit of this function using the graph. So let's go ahead and start with number 67. We would like to look at the limit as x approaches 0 of f of x. So here is 0. And we want to look at the limit as we approach 0 from either side. And it's pretty easy to see that as we approach 0 from the right and the left, we approach this value here, which looks to be 1/4. Excuse me, 3/4. So we can go ahead and write that back on our problem. And we have our answer of 3/4. Okay, the next one we would like to look at is the limit as x approaches infinity of f of x. That means as x gets larger and larger and larger, what does f of x tend to do? So let's go ahead and check that out. And looking at the x values, the outputs as x gets larger and larger, we can see that for very large values of x, our output values are getting closer and closer to the value of 1. So the limit as x approaches infinity of f of x should equal 1. Okay, and finally for our last one, we need to evaluate the limit as x approaches 0 of x times f of x. Now we don't have a graph of x times f of x, but we can make use of one of our limit rules, which states the limit as x approaches a of a function, g of x times f of x, is going to equal the limit as x goes to a of our first function, all times the limit as x goes to a of our second function. So we can simply multiply the limits of each individual function together to get our final value. So looking at number 69, we can see that we have two functions here. We have the x function and the f of x function. So we're going to go ahead and rewrite this limit as x goes to 0 of x times the limit as x goes to 0 of f of x. Now we have to be a little bit careful, because if either one of these don't exist, then this one doesn't exist. So let's go ahead and check this. And the limit as x goes to 0 of x, this is just a polynomial, so we can plug it in, and we end up with 0 times, and we've already figured out what f of x, the limit as x goes to 0 of f of x is, and that's 1. And you can see that right here. So we have our final answer, which is 0. I realize now that I missed one problem, so let's go ahead and take a look at number 61, which I skipped. Here we want to evaluate the limit as x goes to infinity of 1 over x squared. And this is one of those situations in which the numerator of a fraction is going to a number, while the denominator is going to infinity. And so this is going to equal 0. And I just want to talk about this briefly. If you have the denominator getting larger and larger and larger, that's going to make an entire fraction smaller and smaller and smaller, assuming that the numerator is going towards a number. And let's just go ahead and write out some values as we let x get bigger. Let's just start as x equals 1, and if we plug that in, we have 1. If we go to x equals 2, we have 1/4. If we have x equals 3, 1/9. If we have x equals 4, 1 over 16, and you can quickly see that these numbers are getting smaller and smaller and smaller. And as the x grows, they will continue to get smaller and smaller, so they will get closer and closer to 0. And this brings us to the end of the homework.